Thank you very much, Olivier. Thank you to the organizing and scientific committee, and a special thanks to Florence, who made a lot of efforts for making this wonderful event happen. So I'm very happy to present to you some results of my research and of my work, and it will be very much connected to another presentation that we already had yesterday by Niklas Hartung. So it's great because I will be able to go fast on a lot of things that we already saw, because it's the same kind of modeling approach, the same kind of models, and we will see the differences here, because here one important word in the title of my talk is the word surgery, because we will look at some data including surgery of the primary tumor. And the second part of the talk will be devoted to a phenomenon called concomitant resistance. All right, so you already know about this since you've been all very much listening to Niklas' talk yesterday. So metastases can be seen on a CT scan like this. So here it's 2 CT scans with an interval of 127 days, and you have the primary tumor. So here it's the primary tumor is in the liver, and the metastases are in the same organ in the liver, which is not the generic situation that we will consider during this talk, but it's the one that is represented here, and it's sufficient enough to illustrate my purpose, because what I want, the main thing that I see on these two, between these two times here, is that each of the tumors, each of the lesion that is present is growing in size, and you have birth, apparition of new tumor foci. Okay, so one very important thing that we have to keep in mind also when looking at these images is that there are a lot of tumors that are not visible, that are not detectable by, at the imaging, but that are still present. And one of the challenges would be to estimate the amount of invisible metastases from what we see. All right, so metastasis, as has already been said, is a major challenge in cancer today, because it's the main cause of death from the disease. And on the biological side, there has been exciting new biological findings in recent years that are amenable to, I think, a dynamical description and a mathematical description, in particular in the framework of the formalism that I will present to you here. And we will actually focus on the first topic of distant inhibition of angiogenesis by a primary tumor on the metastasis in the second part of this talk. And other phenomena include the self-seeding and the pre-metastatic niche. And for this, you might have seen Etienne's poster yesterday and his recent paper about some really nice biological insights on the metastatic initiation process. But today we will more, I mean, at least for the first part, we will more focus on the clinical challenges of this phenomenon of metastasis, and there are many of them, of course. And so here I have listed four questions that I think can be addressed using mathematical modeling. And so the first one I already told you about is what is the burden of occult micrometastasis at diagnosis from so how to infer this occult burden from what we see, that is only data on the primary tumor, maybe some data on the metastasis, but most of the time, for instance, in breast cancer, most of the time the cancer is diagnosed localized. So this has a tremendous importance for deciding the extent of adjuvant therapy, the amount of therapy that we should give after removing the primary tumor. Another question that has emerged, especially in the last 5 years, is what is the differential effect of therapies on the primary tumor and on the metastasis? Because in some instances, it can be different, and in some instances it can be even very different. In this paper in 2009, John Ebos and Robert Kerbel have demonstrated that some anti-angiogenic therapies might actually accelerate the growth of the metastasis, whereas they were diminishing the growth of the primary tumor. So this is an important topic. I will not present you any result toward in this framework, but the same framework that I present to you is we are working actually with John on this topic. And another question is how to optimize and how to adapt the scheduling and the sequence of anti-cancer agents in the adjuvant setting. All right, so if we look at the breast cancer, canonical example for the talk of today will be breast cancer. And if you look at breast cancer epidemiology, it's a cancer that has a very good 5-year overall survival of almost 90%. However, if you look at survival or if you look at the relapse rates at 15 years, then you see that 28% of the patients that were diagnosed with only a localized disease which has been removed by surgery will relapse with metastatic disease. And even though they have been treated with some adjuvant therapy. So there is still a big challenge in being able to determine which of the patients will relapse from the metastasis and from the ones that won't. And if you look at the 20-year survival, it's only 44%. So it's the same, emphasizing the same thing as above. So if you look at the survival by the stage of the disease, you see these numbers from the SEER database, which confirm you what I was telling you in the introduction, that it's when the disease is metastatic, when you have distant metastasis, that it's lethal. Because when you don't have distant metastasis, then the 5-year survival is almost 100%. And when you do have distant lesions, when the cancer has spread, then that's where it's very dangerous, and only 25% of the patients survive. All right, so this is the outline of the talk. So what I will present to you is a model very similar to the model that Niklas has presented to you yesterday. So I will go fast on this first part, and then we will look a bit deeper into the open clinical questions, the model, confrontation of the model to experimental and clinical data sets, and then implications for the effect of surgery, for assessment of the metastatic relapse risk, and impact of the primary tumor-sided surgery on the survival. The second part will be devoted to concomitant resistance. Okay, so clinical questions. What are important clinical questions that we could try to give answers to? So, for early breast cancer, when it's non-metastatic as diagnosis, the main challenge is how to estimate the amount of residual disease in order to personalize the adjuvant chemotherapy. So and we could think of it in order to identify the patients who will develop metastasis in order to give them a larger number of cycles of chemotherapy, but it's also in the reverse case. A lot of patients do enter therapy, receive chemotherapy, which is very toxic, and we would like to identify patients who have a low risk of recurrence in order to reduce the number of cycles that has to be given to them. And for metastatic breast cancer, when it has already spread, there is as of today no consensus on the utility of the surgery. And so there are actually ongoing phase 3 clinical trials, and there is actually a very recent paper addressing this issue and stating that this is still an open question. So there is a big phase 3 trial by the ECOG that is ongoing. So we still don't know if it's good or not, if it's beneficial for the patient to remove the primary tumor or not. So the question that we wanted to address with this work was, what if the quantitative impact of the primary tumor resection on the time course of the post-surgical metastatic burden? Because if the tumor is already very large and has already spread a lot of secondary metastasis, then maybe it doesn't have any impact to remove it on the total burden in the body. And then the secondary question behind this, but I will not have time to address this, is how to optimize the scheduling of systemic agents. All right, so just a very basic notions of the metastatic biology. So one intriguing fact actually is that depending on the primary site, metastasis can happen in different secondary organs. So for instance, breast can metastasize almost everywhere, to the bones, to the brain, to the lungs, to the liver. But some other cancers have a very specific secondary site of metastasis, such as prostate cancer, that, up to my knowledge, only metastasizes to the bones. So this is intriguing. I will not give any insights on this, but it's still an open question to really understand why is this happening. And the metastatic process is usually described in the biological literature as a sequential process, where you have sequential steps that have to be overcome in order to lead to metastasis. So when you start from a primary tumor that is a neoplasia in an epithelial tissue, for instance, then first you have to undergo angiogenesis. Then there is this. The cells often have a change in their phenotype, so that they can become more motile, and then they enter the blood circulation. They have to be able to enter the blood circulation. They have to be able to survive in the blood. Then they arrest at the secondary site, such as the lungs. They extravasate, and then they have to be able to survive there and grow into detectable macro metastasis. And this actually has been divided, has been proposed to be grouped into two main phases, which are the dissemination and the colonization. So dissemination would be all this part until the arrival in the secondary site, and the colonization will be the colonization of the secondary parenchyma, of the parenchyma of the secondary organ. Okay, so in my view, as in Nicolas' talks yesterday, we will group all the dissemination part in one parameter and all the colonization part in two parameters of growth. So the model looks like this. It's actually very essentialized, very simplified, and it works like this. We have a primary tumor that grows according to a primary tumor growth law, which can be the Gompertz exponential or power law or whatever you want. Usually, we are only interested here in description of the growth of the volume of the tumor. And then it grows and it can spread, it can disseminate some new tumors, some secondary tumors, with a dissemination, according to a dissemination law that depends on the volume, and that will be assumed here to be proportional. So the probability so this is the dissemination rate, meaning that is the probability per day to give a new metastasis, and it will be assumed to be proportional to the volume, meaning that each cell has the same probability within the tumor. And this fundamental parameter here, mu, will be quantifying this metastatic potential. Okay? Then the metastases grow themselves according to a growth law, which may or may not be the same as the primary tumor growth law. So one of the questions that we might be interested in could be to decipher if the growth flow of the primary tumor is the same as the growth flow of the metastasis, and to identify suitable growth flows that could be able to describe data. Okay, so the framework for so I don't want to spend so much time on this. So the framework is basically the same as the one presented by Niklas. I'm really sorry. Each time I go to the SIRM, it's always like this. My curves are not good, so I always increase the size of the lines, but I must have something intrinsically bad in my generation of my plots, because it's never going better. Anyway, so here you should see a growth flow, Gompert's growth flow for the primary tumor, and then so the important thing is that the metastases are formalized mathematically by a density rho structured in volume V. So rho of T and V is something like this. When it's discretized, it looks like a histogram where in the x-axis you have the volume of the lesions, the volume of the tumors, and in the y-axis you have the number of the metastases. So for instance, here we have something like maybe 6, 7 tumors of size between 1 and 10 cells, and then 4 tumors between 10 and 100 cells, and so on. And then the expression of this growth flow of the growth flow of the metastasis translates into a transport equation in the space of the volumes, and the dissemination law translates into the boundary condition, because it's the birth of new metastases at size V0, which will be the size of one cell here. All right? Okay, so I have a movie here where, so here, this simulation has been calibrated for some patient data with some aggressive metastatic potential, which you will see later on how it has been calibrated, but shit. Oh, okay, I will. Where is my mouse? Okay. All right, let me pause here. All right, so, okay, so the primary tumor grows in time, and then it can spread some tumors, which, when they grow in size, they move to the right in this representation of the density of the tumors. Okay, because they start with the size of one cell, and then they grow and they become larger in size, so they go to 10 to the 3 cells, and to the 4 cells, and so on and so on. And you have the spread of, so here, at this time of the disease, you have this amount of metastases which are occult, which are below the detection limit of the imaging device. And okay, and this is the time. Okay, I will not do it again, but at the time, what we should have seen is that at the time of diagnosis, it was still below the whole metastatic mass, which was quite non-negligible, was below the detection limit, and then it would have grown and become larger and become into overt metastatic disease after some time. All right. So now we have our model. We have all the elements in hand, all the framework, and we want to compare and to see if we can fit and if we can infer some information by confronting the model to the data, so to some experimental and clinical data. So what kind of data can we obtain, can we have on metastasis? So it's a hard topic to study experimentally, because since it's an intravitreal process, it's hard to measure. And And one of the technique that is employed is to tag the cells with some protein that is able to emit some light, which is called luciferin, and then you can record the light from the outside, and then this amount of light that is emitted is proportional to the number of cells in the whole organism. So what John Ebos does in his lab, and he's really good at doing that, is that he injects cells at the orthotopic site, so at the primary location, at the usual location of the cancer. So for instance, we will focus here on a breast model, so it's going to be breast cancer cells, actually human breast cancer cells, injected into the mammals of mice, which grow, and then up to some size, and then at some size they are resected. So in order to mimic the real clinical situation, he removes the primary tumor, and then he is able to have a model where there is a spontaneous development of metastatic disease after surgery. So at the end of the day, what we get is some kind of data like this, where we have the growth of so for each mouse, what is important and what is quite kind of precious in this data is that we can follow, for each mouse, we can follow both the growth of the primary tumor and the growth of the total metastatic burden in the same, in each mouse separately. And so we have this kind of data, and this data on the total metastatic burden. So you can already see that it's kind of a challenge then to be able to get some information from it, because you have, even though it's the same cells and all the experimental conditions are made in order to reduce the variability, you still have quite a huge inter-animal variability here. So this is something that we have to keep in mind and to take into account in our modeling. All right. So, okay. So if we take each mouse individually, and if we take all the primary tumor growth data and the metastasis, we can try to fit our model. I will describe. So up to now, I haven't described to you what are the growth terms for the primary tumor and the growth terms for the secondary tumors. I will describe them a bit later, but believe me, with some growth terms that should be specified later, we are able to fit, to have these individual fits, to fit all these. So I think there are, don't remember how many mice in this group, but should be 12, 15 mice, and we fit quite well the dynamics of each individual dynamics of metastatic development. And then, but the main problem with this is that at the end, you will see the model has 3 parameters, 2 for the growth, 1 for the dissemination. And with these 3 parameters, it's quite easy to fit curves like this. It's too easy. It's too easy to fit. And you can see that because you have like a big uncertainty in the estimation of your parameters, meaning that you could have different parameters that would give you the same curves. So, and it's because sometimes you have like only two points or so on. And so in order to improve the quality, the robustness of your estimation, you would like to use this data at the population level. Say, okay, I know that all these mice come from the same population. They have something in common. They are all developing the same process. So, and this, I don't take into account this information when I do the fits individually. And so this is the idea behind the mixed effects modeling approach that was presented by Niklas also yesterday. And so it's in the classical approach for fitting time series, you minimize the least squares when you do the maximum likelihood estimation, you minimize the least squares individually. In the mixed effect modeling approach, what you do is that you say that each theta j, which is the parameter set of the individual j, or the subject j, the animal j here, each of these parameters follows the same law, the same population law, the same distribution. So here, actually, it's not normal. It's log normal in our case. It will be assumed to be log normal. But it doesn't matter. The idea is that all these parameters follow the same law, and then you don't want to estimate each of these parameters individually, but you will estimate the mean and standard deviation of this general law for the population. And then you reduce the number of parameters, or the number of, say, degrees of freedom that you have left to fit from p times n to p plus p squared. And this allows you to improve a lot the robustness of your identification, of your estimation of the parameters. And this is the kind of fit that you can get. So here you have again the data and the model. You have the distribution on the parameters, and from this distribution of the parameters, you can simulate a distribution of model outputs. And then you take the median value of this model outputs and the 10th and 19th percentile, and you can compare it to your data. So this is a fit, and we can try to predict another data set. So here it's in this case, the surgery was performed at 34 days, and when we tried to apply with the same parameters, so the parameters were learned on these data sets, and then we use these parameters for another data set where surgery was performed a bit later at 38 days. It's quite predictive, meaning that when once calibrated, our model is able to simulate at the level of the population to reproduce what happens in vivo in mice. All right. So this has a strong link to what Niklas was explaining yesterday, based on data that were generated by Séverine Mollard and Joseph Ciccolini here in Marseille. Okay, and we can try to predict the survival, and when we do, by saying that the survival time is the time where the metastatic burden reaches a given threshold, and then you can see that we predict quite well the survival. So this is the model survival versus the experimental survival is quite good. All right, so this is the model that was used to do all these fits, and this is the best. I'm saying the best model structure because I tested tons of different ways to change the primary tumor growth law, the secondary tumor growth law, same parameters, different parameters between them, the dissemination law. Maybe you have recognized that yesterday in Niklas' talk, he had a 2/3 power, with the 2/3 power, without the 2/3 power, with different powers, whatever. And you can try tons of different settings. And the best structure, and my definition of best structure, is the best optimal trade-off between the goodness of fit and identifiability of the parameters. So goodness of fit is how well does it fit to the data, and identifiability is these standard errors that you get on the parameters. And what I got from this analysis was that a model with the same growth, so same growth flow for the primary tumor and the metastasis. The growth model was the GAMPEX. You already heard about it yesterday with Niklas. And the lambda here is the in vitro proliferation rate that can be experimentally measured. So John measured this in his lab, and then we could plug this. I mean, it's not a parameter that has to be estimated from the data. At the statistical level, the primary tumor and metastasis were fitted all together. Proportional statistical error model, log normal, population distribution of the parameters, and computation of the total metastatic burden was made very easier, using the fast Fourier transform algorithm, as Niklas was explaining yesterday. It's an important part of the thing, because you have to do this to minimize the likelihood, to maximize the likelihood. You have to run the model a very large number of times. Okay, so these were for preclinical data, experimental data on mice. What about humans? So in humans, you don't have so many data, because you cannot inject tumors to humans and make them grow and then look at the metastasis, right? So but there is still one interesting data set of more than 2,000 patients, breast cancer patients, that were diagnosed with a primary tumor, localized primary tumor of the breast, And what was performed in this study is that these patients were followed during 20 years. They did not receive any adjuvant therapy. It was several times ago, and they were followed in time for 20 years, and then stratified by the primary tumor size, which is quantified here by the diameter. The investigators reported the percentage, the proportion of patients that did develop metastatic disease during the next 20 years. So what you can see on the data here is that it's larger, the probability to develop metastasis is larger when the size is larger, but the second interesting thing, and very interesting thing here, is that it's not all the patients that have, for instance, primary tumor between 2.5 and 3.5 centimeters that develop metastatic. Only 40% of them will have metastatic relapse. So the question was, okay, in our model, we have reduced, and we have made everything to do that. We have made the model minimally parameterized in order to have the minimal number of parameters for quantifying the metastatic potential. So the question was, would we be able, with a variability on this metastatic potential parameter, would we be able to reproduce all these percentages just with the distribution of the metastatic potential in the population? And the answer is yes. So I will skip the technical details because we have to fix, of course, the kinetic parameters and then define what is the probability of having a metastasis as being the probability of having already one at diagnosis. But at the end of the day, what you have is that, here it's a log normal distribution of just mu, not gamma, and it's not m. Is that the fit is it's a fit, but it's very well, it's very good. You can reproduce the data very well. So, and it's significative. You can run a statistical test to see if you're not overfitting. And yes.
Three parameters you were fitting, the one we talked about before.
Only one, only a distribution in the population of mu. So there are two parameters. There is the mean value of mu and the standard deviation. That's it. And you have 1, 2, 3, 4, these data points. And this test tells you that you don't have more parameters that you need to, Okay, and I'm sorry, we don't see anything on this table. But what you should see is yeah, it's really bad looking. Okay, so here it's a table with all the parameters in different settings. So you have the in vitro, the in vitro for the breast, let's forget about it, but we had one model for preclinical breast, one animal model of preclinical breast data, one animal model of preclinical kidney data, and the clinical breast data. And what was interesting, you will not be able to see here, is that the mu, the median value of mu that was estimated for the animals in the breast, but it's human breast cells injected in the animals, the value of mu was very similar in the animal model as in the clinical data. And again, so I want to emphasize that this value of mu is fundamental and could be very useful for personalization of the diagnosis and of the therapy. If you take this calibration of the mu in the population, if you take the median value of mu, then you have, when you do the simulation, you predict that a patient with this value of mu would have only 2 metastases, which are relatively small, whereas with a large value of mu at the level of the 90th percentile in the population, you predict that there would be a huge occult metastatic mass. And the different, the thing is that in the two cases here, all the mass is below the imaging detection limit, so you would not detect anything. So these two patients would be diagnosed T1 N0 M0, which is basically the same, the same category. However, of course, it might be a good idea to adapt the adjuvant therapy differently between these two patients, because you want to give more cycles of chemo to this one than to this one. Okay, and the last slide on this part of the talk is about the influence of the primary tumor size at the time of surgery on the survival. So what was performed here was to run a simulation study where for various size of the primary tumor, we simulated the model where the primary tumor is removed at this size, and then the metastases grow by themselves, and then we can compute the survival as the time to reach a lethal burden of 10 to the 12 cells. And what you can see, what is interesting in these results is that the curve is actually very nonlinear, meaning that it's not a line, and you have a whole area where below some threshold, some first threshold, you basically have this is a threshold where you have no metastasis at diagnosis. So this is for a median value of mu. Below this threshold, you have no metastasis at diagnosis. So basically, you have a negligible recurrence risk. Between this threshold and this threshold, then depending on the size is very informative on the probability of having a recurrence. And above some threshold, when the primary tumor is too large, then the size is still not very much informative, because the relative survival, the benefit between removing the primary tumor or leaving it is less than 10%. All right, these are survival curves that you can simulate, and this is a table of the value of these thresholds depending on the value of mu. Okay, so to summarize, what I presented to you up to now is a biologically based, minimally parameterized mathematical model for the metastatic development that was able to link the pre-surgical primary tumor growth to the post-surgical metastatic burden dynamics. It was validated, or at least was confirmed to preclinical and clinical data sets. And what we could infer is that we could describe the data with the same growth law between the primary tumor and the metastasis, equal probability among the primary tumor cells of successful establishment of a distant colony, and no secondary dissemination by the metastases themselves. As I wanted to really emphasize, and that's a critical thing that I want. One thing that we believe in very much with this model is this parameter mu. We think that and we think that we could have some good ways to calibrate this using some genetic expression data on the primary tumor, and it could be a great way to estimate in a patient-specific way the probability of metastatic relapse, but not only that, several things, and this nonlinear dependence of the survival on the primary tumor size. Okay. Then I have a small comparison with what Niklas was saying, because in Niklas' talk yesterday, the main difference is that he had no surgery. So there are very different. There are several things that make that the quantitative comparison between the two data sets or the two studies is not very relevant. Is not completely doable because of several technical aspects. But still, if you take the same framework as he had and you apply it to our data with the surgery, what we found was significantly larger of the parameter A, which is a parameter here in the Gampert's law. So it's a growth velocity. It's linked to the proliferation rate. And so this could suggest a post-surgery accelerated growth. Related to Jean's question yesterday, it's an indication of this. But also we also found a smaller metastatic emission parameter. And this could be due to the fact that in their case, the animal model was much more immunodepressed than in our case. Okay, so now the second part of my talk, I would like to talk to you about concomitant tumor resistance. So what is concomitant tumor resistance? This is a phenomenon where the presence of a primary tumor, of one tumor, inhibits the growth of a secondary tumor. And this is actually something that is not new. It's not very known. I mean, it's not very famous, at least. But it has been evidenced more than 100 years ago. And the primary hypothesis that had been proposed was that this first tumor it eats the nutrients and it doesn't leave the nutrients enough to the other tumor, and so that's why the other tumor doesn't grow. Another hypothesis was and it was termed concomitant immunity, was that the presence of a primary implant of a first tumor stimulates the immune system so that it's already stimulated, and when there's a secondary tumor, it inhibits the growth of the secondary tumor. But it was discovered that it happened in immune-deprived mice in the 80s, invalidating this hypothesis. So that's it. And in the 90s, there is this seminal work of the team of Judah Folkman, where they were looking a lot at this thing because, so as you probably know, Judah Folkman played an important role in the discovery of the importance of neoangiogenesis and its inhibition in tumor growth. And in this paper in 1994, they discovered some endogenous inhibitors of angiogenesis, which are molecules that are produced by the primary tumor itself that are able to inhibit angiogenesis locally, but also distantly. So maybe this inhibition of a secondary growth could be due to the release of these inhibitors that would go systemically inhibit the secondary tumors. And this is very linked to the phenomenon of post-surgery metastatic acceleration, because, of course, if you have an inhibition force between one tumor, between the primary tumor and the metastasis, if you remove the primary tumor, then you suppress this, when you remove this inhibition force, and then you might have this burst of the metastasis. So this is a major challenge, and it has actually been evidenced clinically in some patient cases reports. There hasn't been, up to my knowledge, large studies confirming or infirming or identifying in which cases this happened and in which cases this doesn't happen. So you have some clinical data that support this hypothesis, and some preclinical. So in animal experiments, it has been reported and evidenced in a lot of settings, in a lot of studies since the oldest one that I found was from 1910. So yeah, it could be due to the surgical trauma itself, but some experiments were also like doing the trauma in their control group, the trauma. And experiments suggested other hypotheses linked with the metastatic dormancy, which is this escape from dormancy when you remove this inhibition force from the primary tumor. Of course, linked to the concomitant resistance I was telling you before. So if we look at some data, so this study is the study from O'Reilly and Folkman, this paper from 1994 in Cell, when they discovered the molecule endostatin. And what you have on the left, so this is a slice of a lung, and what you can see here is that when the tumor is present, you have only micrometastases that are localized around blood vessels. And when the tumor was removed, then in the lungs, you have huge micrometastatic mass, highly angiogenic. The brown staining here stains for endothelial cells, so for angiogenesis. So the objectives were to try to give a mathematical description of the dynamics of this process. Again, a minimally parameterized, biologically database mathematical model of the process, and ideally to test these hypotheses, to translate all these hypotheses that I mentioned into different mathematical models and see if we could infer from experimental data, if we could discriminate and reject some of the theories. So this was back when I was doing my postdoc in a biology lab. So what was great is that I could go to my boss and say, okay, I really want to study concomitant resistance and post-surgery metastatic acceleration. And she said, okay, yeah, we can do the experiments. So we did the experiments, and the experiments consisted in to inject 2 tumors with the same number of cells at the beginning, 10 to the 6 LLC, so it's Lewis lung carcinoma cells in immunocompetent mice. So it's a murine, it's a murine cancer in mice. And we will look here at 2 groups. The control group had only 1 tumor, and the simultaneous group had simultaneous injection of 2 tumors in the back at the same height of two tumors. And we will record tumor growth in time at the 2 sites. Okay, so we did some with other investigators at the lab. We did some bets about what would happen. And there was a biologist, Nava is a biologist, Janula is a clinician, Kathleen is a modeler, and me, I'm a modeler too. So Nava predicted that nothing would happen, basically that the experiment would be a failure. Janula predicted that, so the red curve is the control, and the 2 blue curves are the two tumors in the simultaneous group. So she said one of the tumors will grow the same as the control, the other will be inhibited. Kathleen said the 2 tumors will be inhibited and will grow the same, and I said they will be both inhibited, one will one stronger than the other. So I don't know, but we could make a small poll here. And we could make a small bet here. So who believes that what will happen is Nava's answer? Someone? Yeah, good answer. Who believes Janula's? 2, 3, 4. 4 people with Janula. Who believes Kathleen? Okay, nobody. Who believes me? Come on. Thanks. Okay, but I was wrong. What happened? Sorry for the image. What happened was this thing. One tumor grew bigger than the other, and the other and so one tumor grew the same as the control, and the other grew smaller. So these are the results on the growth curves that you can see here. You have typically this situation of one tumor growing, the other being inhibited, except in this case. So in these 9 mice, there is only 1 mouse where this did not happen. It's actually funny because on the data we could see that there was some small blood vessel that was linking the 2 tumors. And if you look at, if you compare to the control group where you have only single tumors, then you can already see that here you have a much wider spread scope in the growth curves. If you want to do statistical confirmation of this fact, then it's a bit tricky, but I will summarize here. But this says that the large tumors were behaving the same as what would as in the control, and the small tumors were significantly smaller than than the controls. Okay, these red dots here stand for statistical significance. So this is what happened. I will skip this, and so then I wanted to do some model that would be able to fit that. Okay, this I will skip. The first idea was to say, okay, we will do some symmetric inhibition, but some asymmetric inhibition. One tumor, we will just say, okay, one tumor inhibits the other. But this is not very biologically. This is not very relevant because it was able to fit the data, but it's not very relevant because you impose by yourself from the beginning that there is one tumor that inhibits the other, but you have no way to choose from before. So we have, if we want a biologically consistent theory, we have to assume that if there is inhibition if there is a direct inhibition force between the two tumors, it has to happen with the same parameter and symmetrically between the two tumors. So this is this model. But still, there has to be some difference at the end of the day between the two tumors. So maybe it could come from stochastic fluctuations in the initial number of cells that take. Maybe in one of the two tumors, a little bit more of the cells take, and in the other tumor, not a little bit less of the tumors take, and maybe this small difference can be amplified into big differences when in the dynamics, but with the same inhibition force between the two. So this is the second theory. We could also, so yeah, sorry, I don't explain in detail. This is the Gompertz growth, the Gompertz term for the growth, and then inhibition term. We could also do the same, but using the Hennenfent model for inhibition of the growth, meaning that it's indirect inhibition of the growth through angiogenesis, so through this model. And we could model the competition between the two tumors, the atherpia hypothesis, by having this Gompertz, where here instead of the V1 and V2, we have the sum of the two volumes. So again, an important thing in all these models is that we always want. I mean, we don't let the parameters to be different for the tumor 1 and tumor 2. We have always the same parameters for tumor 1 and tumor 2. So same A here, same A and B and D here, and so on. So the best model in terms of biological relevance and goodness of fit and identifiability of the parameters was the model with direct inhibition. So it's what you can see here. And so it fits quite well all the data with only, I think, it has maybe 3 parameters. And the dotted curves are the curves when E is equal to 0. So you see that you reproduce some realistic curves that could be the control curves with E equal 0. And with E non-zero from the fits, you have this difference in inhibition. And you also test that it's not an artifact of just the difference. Just the difference in V0 only gives you this difference, whereas when you put the inhibition, then you really explain the difference in the growth. But on the other hand, the competition model was also able to fit. And all these models actually were able to fit. And okay, I skip this. You can quantify the goodness of fit of the models through some statistical metrics. So the best model according to this metrics is the direct inhibition model, but I don't trust that much these metrics because it's some arbitrary way to measure this. When I see something that has a good R-squared and that fits well visually, I cannot say that I can reject the theory, even though another model can do better. These are the parameter values, and you can see that you have good standard errors on the these are normalized standard errors on the parameters estimation, and you can compute from this. You can compute some 95% confidence interval, and you see that you identify a non-zero confidence interval for the inhibition parameter, and the V0. Yeah, I haven't put it here. Yeah, V0 second has. I mean, all this makes sense when you look at the values. Biologically, it's plausible. And yeah, and to summarize this, so to finish this last part. The main result, which was already seen in, without the modeling, is that in a mouse bearing 2 tumors implanted simultaneously, growth was impaired in one of the 2 tumors and not in the other. We have developed some models that are robust, let's say, for description, at least description of this phenomenon, which might be very interesting for integrating this model into the global metastatic model in order to simulate the metastatic dynamics when all the tumors would be interacting in the system. And yeah, I would really like to thank all the collaborators, all the experimentalist collaborators on these works that did all the data. Without it, nothing would be possible. So John Ibos from the Roswell Park Cancer Institute that was furnishing all the preclinical data of the ortho-surgical animal models of metastasis, and the 2-tumor study was performed in the Center of Cancer System Biology. And Claire Lamont was the technical assistant that helped me doing the experiments and spent so many time doing this, and Philip Hanfeld and Lil Latke, which were my advisor there. I thank you very much for your attention, and I will be happy to have any questions.